In the previous video, we talked about colligative properties. We discussed how adding a solute changes the properties of a solution, and we specifically took a closer look at boiling point elevation and freezing point depression. Today, we're going to try and accomplish two things. The first is to introduce equilibrium in a way that's easy to understand, since this is a concept that we will revisit many times. In addition to this, we need to cover the remaining two colligative properties, vapor pressure and osmotic pressure. Before we get into any of that, it'll be helpful if we do a quick review of the concept of pressure. Pressure is essentially just a force that is applied over an area. When we talk about air pressure, we mean that the air above us is pushing down on us, exerting a force on us, and we call that force air pressure. We'll want to keep this definition in mind as we move forward. First things first, what is equilibrium? The technical definition of equilibrium is as follows: the point at which a system becomes stable. The word stable here denotes a state where the system is not fluctuating or changing. A system is any region of space or matter that is selected for study. The surroundings are everything that's, surrounding the system. In most cases, this means the rest of the universe. Here's a practical example. Let's say an ecologist is trying to study the different animal and plant species that live inside a lake. In this case, the ecologist's focus is on the lake itself. He or she might also take the lakeshore into account, so we can say that in total, both the lake and the area immediately around said lake comprise the system for the purposes of this ecological study. The surroundings, then, is the rest of the universe exclusive of the lake and its surrounding area. Everything outside the area chosen for specific study is the surroundings. In chemistry specifically, a system is said to have reached equilibrium when a process and the inverse of said process are happening at the same rate. This leads to the system as a whole staying the same, since the respective processes are, in effect, canceling each other out. A real-life example of this can be seen on a treadmill. Imagine a person running on a treadmill. Anyone who has ever done this can testify that a person running on a treadmill isn't actually going anywhere. Their location is not changing. And the reason for this is that the treadmill keeps pushing them backwards at the same rate that their legs are pushing them forwards. The forward force and the backward force are the same, and since they are pushing in opposite directions, they cancel each other out. This is why a person running on a treadmill doesn't actually move through their room or the gym where the treadmill is located. The person can therefore said to be at equilibrium, and a system which is trying to study the movement of this person through space would conclude that the system itself is at equilibrium. Why? Because the process of moving forwards and its inverse, the process of moving backwards, are canceling each other out. Another example, more relevant to chemistry, is that of a bottle of soda or pop or cola or whatever we'd like to call it. Any carbonated beverage is going to contain carbon dioxide gas that is trying to escape into the surrounding atmosphere. If the rate at which carbon dioxide in the air is moving into the drink is the same as the rate at which carbon dioxide is trying to escape the bottle of beverage, the concentration of carbon dioxide in the drink is not going to change. The upward motion of carbon dioxide from can to air is the same as the downward motion of carbon dioxide from air to can, or air to bottle. The system is at equilibrium. Of course, this is very rarely the case in real life. Most of the time, the rate of evaporation of carbon dioxide is greater than the rate of carbon dioxide absorption by the beverage, which is why a bottle of soda left opened will eventually lose its carbonation and taste flat. That should give us a good foundation for the theoretical concept of equilibrium. Now let's apply that understanding by looking at vapor pressure and osmotic pressure, starting with the first. Imagine a system consisting of a gas cloud floating above a liquid. That gas, like atmospheric air, is going to exert pressure down on the liquid. At the same time, the liquid is going to exert a force on the gas. If anyone has taken physics or has any background knowledge about classical mechanics, they might remember Isaac Newton's third law of motion. Every action has an equal and opposite reaction. This is a good explanation of equilibrium in general, as it happens. To understand this in relation to our gas cloud and the liquid beneath it, imagine what would happen if the force the gas was putting on the liquid was stronger than the force the liquid was putting on the gas. What would happen? The liquid surface would be pushed apart. If the force of air pressure on concrete was stronger than the force the concrete was putting on the air above it, the air would split the concrete in two. For either system to remain in a state of unchanging constancy, the forces have to be equal. So, when the force the gas is putting on the liquid is the same as the force the liquid is putting on the gas cloud, that pressure is called the vapor pressure. Another way of saying this is that the vapor pressure is the pressure experienced at equilibrium. We should note that a higher vapor pressure is indicative of a substance that readily transitions to being a gas. Chemists will sometimes call this volatility. A highly volatile substance will most likely be a gas, even at room temperature, whereas a substance with a lower volatility and a lower vapor pressure will probably be a liquid or a solid at room temperature. Also, adding a solute decreases the vapor pressure of a solution. Pure water has a higher vapor pressure than salt water, for instance. The scientific reason for this is that the presence of solute molecules in a solution means that there is less room for solvent molecules to reach the top of the solvent surface. It's easiest to understand this in relation to a system in which the solvent is a liquid and the solute is a solid, but we can apply the same concept to any solution. Less solvent molecules on the surface of the liquid means less pressure is exerted by the liquid on the gas, and this lowers the vapor pressure. This phenomenon is very creatively named vapor pressure lowering. Our fourth and last colligative property is osmotic pressure. The term osmosis describes the movement of solvent molecules from an area of low solute concentration to one of high solute concentration. Why do solvent molecules do this? It all comes back to that concept of equilibrium. In nature, forces naturally want to move toward equilibrium. Let's imagine a bucket of water. Someone comes by and tosses a handful of sugar into the water. Sugar is the solute, water is the solvent. At the moment that the handful of sugar hits the surface of the water, the concentration of sugar is highest at that location. There's no sugar at all in the water at the bottom of the bucket. If we wait a minute or two, the sugar molecules will disperse and more or less equally distribute themselves throughout the whole bucket. Each region, or area of the bucket, from the top, the middle, and the bottom, will contain a similar concentration of sugar molecules. At this stage, the system has reached equilibrium. There isn't a mass migration of sugar molecules from one part of the bucket to the other. Osmotic pressure is the amount of force we would need to prevent this stabilization of the system. If we wanted to keep all the sugar molecules in the top half of the bucket and pure water in the bottom half, it would take a certain amount of force, and that amount is called the osmotic pressure. Usually, keeping a solute in one region of a solvent is done by adding a membrane. In just a minute or two, we'll see a visual illustration as to how this works. But conceptually, adding solute increases osmotic pressure, and this is the logic behind that. More solute means that there will be a greater difference in the concentrations of solute in the high concentration region and the low concentration region. There is a larger disparity. This larger disparity compels the solvent molecules to try harder to move from the low concentration region, to the high concentration region. This means more pressure will be necessary to stop this movement, and this results in higher osmotic pressure. Mathematically, osmotic pressure is calculated with an equation known as the Van 't Hoff equation, which is named after Dutch physical chemist Jacobus van 't Hoff. The equation is shown here. The term OP is osmotic pressure. I is a constant known as the Van 't Hoff factor. R is another constant called the ideal gas constant, and T is the temperature measured in kelvins. For most solutes in water, the term I is equal to 1. The ideal gas constant R has different values depending on which units we use, but a commonly used value is 8.314 kilograms times meters squared all over seconds squared times kelvins times moles. Another value of R we will encounter frequently is 0.08206 liters times atmospheres all over kelvins times moles. Let's look at what happens visually in regard to vapor pressure and osmotic pressure. For vapor pressure, let's draw out our gas and liquid system. Here, we have a lake. Above it is the atmosphere. The lake is liquid, obviously, and the atmosphere is a gas mixture. The atmosphere is pressing down on the lake. At the same time, the lake is pressing upwards on the atmosphere. Every action has an equal and opposite reaction, remember. As we're looking at it now, the lake and the atmosphere are at equilibrium. The amount of pressure that the atmosphere is exerting on the lake at this moment is the vapor pressure of the atmosphere. Now let's look at a second lake. We'll label this one Lake A, and the second one will be Lake B. Lake B is a saltwater lake. So, along with the water in the lake, we also have little sodium chloride molecules dispersed throughout the liquid. Of course, the more or less even dispersion of salt molecules means that some of said molecules will be floating near the surface of the lake. If we were to measure the force that the liquid, by which we mean the water molecules, is exerting on the atmosphere, the force would be lower for the water in Lake B than the water in Lake A. To remain at equilibrium, the atmosphere would not be exerting as much pressure on Lake B as it is on Lake A. Thus, the vapor pressure of the atmosphere on Lake A would be higher at equilibrium than the vapor pressure on Lake B at equilibrium. Again, the key phrase here is at equilibrium. If either system is not at equilibrium, the atmosphere can exert varying levels of force on the lakes. But at equilibrium, the atmosphere would press down harder on the water in Lake A than the water in Lake B. Osmotic pressure is next. Let's draw our bucket of water. In our first scenario, a person tosses in a handful of sugar. Over time, the sugar molecules evenly disperse throughout the bucket. Measuring the molar or mass concentration of sugar at any area inside this bucket would yield the same answer. Now let's imagine a second scenario where a membrane is stretched through the middle of the bucket, effectively dividing it into two regions, a top region and a bottom region. This membrane is called a semi-permeable membrane because it allows certain compounds to pass through it while others are stopped. When we describe something as permeable, we mean that it allows substances like water, for example, to pass through it. Semi-permeable means that certain substances are allowed through, while others aren't. Let's say that this semi-permeable membrane allows sugar molecules to pass through while stopping water molecules. The membrane itself is added after the sugar is thrown in. This means that the concentration of sugar in the top region is higher than the concentration of sugar in the bottom region. In order to restore equilibrium, the water molecules in the bottom region will try to push through this membrane and enter the top region. The amount of pressure exerted on the membrane by these water molecules is called the osmotic pressure. Adding more handfuls of sugar to the top region will simply increase the efforts of the water molecules to pass through, increasing the osmotic pressure experienced by the membrane. It should be noted that the important point to remember here is the qualitative effect of adding solute to a solution. We shouldn't neglect the math, but the concepts are what we should focus most of our attention on. To wrap up, adding a solute to a solvent changes certain properties of the resultant solution. The properties that change are called colligative properties. The four colligative properties are boiling point, freezing point, vapor pressure, and osmotic pressure. The addition of solute increases boiling point and osmotic pressure. Conversely, adding more solute decreases freezing point and vapor pressure. These effects are the most salient points from this video as well as the one preceding it. We'll end this video with one worked example showing the Van't Hoff equation in action. The mathematical relation that relates vapor pressure to solute concentration is more complicated, so we'll reserve it for our unit on thermodynamics. Our example here says, sugar water is prepared by dissolving 30 grams of sucrose in 100 milliliters of water. What is the osmotic pressure of the solution at 25 degrees Celsius? Let's start by writing down our equation. We're trying to find osmotic pressure. It's reasonable to assume that the Van Hoff factor is 1 in this case, since the solvent is water and the problem statement doesn't say anything to the contrary. For the ideal gas constant, we'll go ahead and use the value 0.08206. The molarity of the solute can be found through a calculation we know well. First, we need to convert grams of solute into moles of solute. The molar mass of sucrose is about 342 grams per mole. 30 grams divided by 342 equals about 0.088 moles. This is then divided by the volume of solution as expressed in liters. 100 milliliters is equal to 0.1 liters. And 0.088 divided by 0.1 is equal to 0.88 moles per liter, or 0.88 m. Our final step is to convert 25 degrees Celsius into kelvins, which we do by adding 273.15 to 25, obtaining 298.15 Kelvin. All that remains is to multiply these variables together. Our final answer is 21.53 atmospheres, where atmospheres is a unit of pressure. Again, this is the osmotic pressure, which means that it will take 21.53 atmospheres worth of force to keep solvent molecules from moving from an area of low solute concentration to an area of high solute concentration within this system involving a sugar-water solution. If we were to add more sugar and thereby increase the value of the variable m in the Van Hoff equation, the value of osmotic pressure would increase. And this is an easy thing to prove algebraically, since there's a direct relationship between these two variables. This is basic arithmetic, actually. Increasing the values of factors in a multiplication problem will always increase the value of the product, and that's what's happening here. In the next video, we will explore the molecular mechanics of solvation. Thank you for watching.